Welcome back to the Colloquium and welcome to the new academic year. We're very glad to see all of you here and especially also all the new faces. Today's speaker is visiting Anastasia, so I'm going to hand over to her for an introduction while I press some buttons over here.
Okay, thanks for coming. It's really exciting to have Viraj Pandya as our first speaker of the academic year. Viraj actually did his undergraduate in economics in Rutgers and then did a loop in the air and a year of program in Princeton to convert to an astrophysicist. And then he did a PhD in astrophysics in University of Santa Cruz in California and Flatiron, so a joint program. And now he's a NASA Hubble Fellow in Columbia, so very steep growth curve. And Viraj is an expert on observational, computational, and theoretical astrophysics, working on galaxies in cosmological context. So the floor is yours. Yes, I forgot to mention that his research was actually featured in New York Times about galaxy going bananas, so I hope we will hear about it today.
Awesome. All right. Thank you so much, Anastasia, for the very nice introduction. It's great to be here. Very surreal, actually, to be giving the first colloquium at the Institute of Astronomy here in Cambridge. My first time actually in the UK. So thank you so much for having me and making this possible. So I'm very excited to share some new puzzles in galaxy formation based on my recent work with the James Webb Space Telescope on the 3D shapes and alignments of early galaxies. Before I get started, I want to just introduce myself a little bit. So as Anastasia said, I'm a NASA Hubble Fellow at Columbia in New York. What that means is that NASA wants me to work on research using their telescopes that addresses fundamental questions about our cosmic origins, like how do we get here? It's a very broad question, so I'm going to split it up into three smaller ones that connect to my work. So the first is, of course, what is the universe made of? So I'm a central collaboration member of this Simons collaboration on learning the universe, headed by Greg Bryan at Columbia. And we're interested in inferring not just the cosmological parameters, but also the initial conditions, the actual distribution of the amplitudes and phases of the density perturbations that eventually gave rise to the exact clustering of galaxies that we see around us. So on that note, with my colleagues in this collaboration, we're also working on new approaches for doing Bayesian reconstructions with very fast AI-accelerated simulations. So this is on the left here an example projected density field of galaxies from the 2MASS survey with the Milky Way at the center out to about 300 megaparsecs. And then these are simulations drawn from a constrained posterior where you can see within the region where we have data that was used for the inference, we can basically reconstruct the redshift zero clustering of galaxies, and then beyond that, it's just very uncertain. I will not talk about either of these two things today. Instead, I'm going to talk about the third fundamental question that I work on, and that is how did galaxies like our own Milky Way form? And again, this is going to be based on my work with JWST on the 3D shapes and alignments of high-redshift Milky Way progenitors, very broadly defined. So let's go back 100 years to Edwin Hubble's APJ journal in 1926. If you go read his paper, there's one key line where he says that there are many more galaxies nearby that appear round or nearly round than can be accounted for by randomly oriented disk-shaped objects alone. This is, of course, one of the things that he used to justify his development of the Hubble sequence, or the Hubble tuning fork diagram, right? Where if you're seeing lots and lots of round galaxies, he said there must be a class of intrinsically round or spheroidal, these elliptical galaxies in the local universe. And then you've also got these spirals that are organized based on the prominence of their spiral arms and the absence or presence of a stellar bar. About 35 years ago, right, the famous telescope that was launched, named after Hubble, made many great discoveries. And one of, I think, the coolest things that I think is maybe forgotten these days is that when astronomers were planning some of the first kind of proto-Hubble deep fields, they discovered that not only were high-redshift galaxies typically star-forming in blue, they were also typically often elongated and very linear-looking. And Cowie et al. In '95 called these things chain galaxies because many of them were also very clumpy, with clumps arranged in linear-like pattern. In the mid-2000s, a very nice paper by the Elmegreens with a tidal where that just explains the result. As you approach the detection limit of Hubble imaging, at the time, you're dominated by these linear structures. So these chain galaxies dominate over the zoo of other galaxy morphologies that we see in the early universe. It wasn't until the early 2010s, after the installation of the Wide Field Camera 3, a near-infrared camera on Hubble, which could look at early galaxies at rest frame optical wavelengths, right, in the near-infrared, and the completion of huge surveys like CANDLES and 3D-HST, that observers like David Law and my collaborator Arjan van der Wel really were able to show statistically with large samples that if you look at the distribution of the projected axis ratios of high redshift, say redshift 2, low mass galaxies, these distributions look very asymmetric and they're skewed towards small or edge-on axis ratios. There's many more elongated galaxies than there are rounder objects seen in the early universe at low masses. This is not what you see for massive galaxies. This is relatively uniform distributions. We think these are a combination of just randomly oriented massive disks and ellipticals. You also don't see this for the low redshift population. So for example, from the SDSS survey, here again are the distributions of this projected axis ratio for these same mass bins at low redshift, and again, they're pretty much all relatively uniform. You don't see these kinds of exotic distributions for low redshift dwarfs. So we'll come back to that later. So let me now map out a landscape of possible explanations for this puzzle. So the first and probably safest bet is that we're seeing this excess of elongated galaxies in the early universe because of surface brightness selection effects, right? So we've known for a long time that it's much easier to detect and characterize an edge-on disk, right, where the light is concentrated in a thin plane, as opposed to a face-on disk where the surface brightness, especially in the outer parts, is going to be lower, right? And also at high redshift, the disks themselves are often very clumpy, so these high redshift clumpy disks can themselves masquerade as these edge-on chain galaxies. So this is one, a lot of astronomers are in this camp, but there's another camp of astronomers which says, well, actually, hold on, this might be evidence of intrinsic 3D geometrical evolution, such that as you're going towards high redshift galaxies at low masses, they're not starting out like axisymmetric or circular disks like the ones that we're familiar with in the local universe. Instead, they're significantly flattened along a second axis. So they're shaped like these prolate ellipsoids or like these triaxial ellipsoids, which we'll come back to later in this talk. This might sound very exotic to you, but it shouldn't sound exotic. We know of things that are shaped like this in the local universe. They're part of massive disks. They're called stellar bars, right? And we see examples of bars and massive galaxies at high redshift, now with JWST, but our low mass chain galaxies, they are not massive disks. We don't see evidence of, a bright, massive stellar disk component out of which you can get secular bar instabilities to form these kinds of elongated structures. And also our things are probably dark matter dominated. So it's not wrong to say that we're seeing, pure bars essentially, but there's more to the story that'll become clearer later in this colloquium. And the last thing is, well, the early universe is also very messy, right? And so are we just seeing tidal debris from ongoing galaxy mergers, right, leading to these elongated structures? Or what is the role of dynamical instabilities in disks or in these elongated prolate or triaxial structures? So we'll come back to this throughout the talk. But for a second, I want to just say, it's been 30 years since chain galaxies were first discovered, and we don't have a definitive explanation for the relative contributions of these different possible scenarios. And so enter JWST, which launched right as I started my Hubble Fellowship at Columbia. At the time, and even now, I was working mostly on the theory side of my work, kind of breathing new life into these semi-analytic models of galaxy formation. And so, using, for example, hydro simulations to understand gas flows, develop simple models for that. Also develop models for galactic atmospheres and how to couple feedback to the large-scale gas surrounding galaxies. Developing new AI-accelerated models of this type to then really enable new ways to do inference for galaxy formation and cosmology. And all this work has been very interesting, and it led to me becoming the PI of a large grant from the National Science Foundation. to also rethink satellite galaxies and how they evolve around Milky Way type hosts and also more massive groups and clusters. So I was deep in the middle of all this in 2021 and 2022 when then I saw these amazing papers come out from many of the early release science collaborations for JWST. So for example, this nice paper by Dan Eisenstein and the JADES collaboration, where JWST, they showed, picks up very easily this obvious face-on spiral galaxy that was just completely missed in older HST imaging. Right? A nice paper by one of my former mentors at Santa Cruz, Brant Robertson, which also showed using machine learning the discovery of all these disk-like things at high redshift that were just missed by Hubble. And then the paper that really got my attention was this one with the sensational title, which I love, Panic at the Disks, Like the Band, right? Where they convincingly showed, according to their analysis, so the disk fraction in HST is dropping off dramatically as you go to high redshift, but then the disk fraction, according to their JWST analysis, is actually much higher at the 40 to 60% level. So this is very interesting, but it really begs the question, so JWST is detecting these disk-like things, but what do you mean when you say disk, right? So typically in a lot of these studies, you're doing visual classifications of individual galaxies one at a time. And in the case of something like this, it's fine. I mean, this is obviously a face-on spiral. These things, I don't know exactly what they are. Right? So motivated by that, I'm also very lucky to be a member of one of these early release science collaborations known as CEERS, the Cosmic Evolution Early Release Science Survey. In fact, I got involved in CEERS during the proposal writing process as a first-year grad student at Santa Cruz. One of my mentors, Sandy Faber, got me as an Osterbrock Leadership Fellow to shadow the PI, Steve Finkelstein, a professor at UT Austin, who was newly appointed to lead the CEERS team of 100 people and more. And so on the top here, back in the summer of 2022 when we got our first data, I just made some of these plots and I was just blown away. So on the top is some of the deepest imaging that we had from Hubble in 2022 from the Candle survey. 50 hours of integrating on the same patch of sky, some of these elongated, high redshift, low mass galaxies. And then in less than 1 hour with JWST for the same galaxies, you see so much more internal substructure and even some neighbors that were missed by HST in the past. So with this exquisite data, my CEERS colleagues and I wanted to go and revisit the question of the origin of these chain galaxies, right? So here is CEERS. It's one of these, what's known as a pencil beam survey. It's a tiny, tiny fraction of the sky in which we have very deep observations. So it's next to this rectangular field next to the Big Dipper. This is old Hubble imaging. You can zoom in, you see thousands and thousands of galaxies, right? And so what we did is we essentially fit every galaxy, its two-dimensional light distribution, to characterize every galaxy by the projected axis ratio of its light distribution at the radius that encloses roughly half its integrated light, right? So this ratio, again, B over A, right, is the ratio of the semi-minor to the semi-major axis of the best fitting ellipse at the half light radius. And when this ratio is small, it means the galaxy is very elongated in the sky. When the ratio is close to 1, large, the galaxy is very round in the sky. So we did this for all the galaxies in our JWST imaging. And then we just did a very simple counting exercise, right? For galaxies of a fixed mass, fixed redshift bin that are star forming, that are comfortably above our surface brightness detection limit, what is the distribution of B over A now with the much more powerful and sensitive JWST? And much to our surprise, we see these same very strange asymmetric distributions of B over A. This is an example for one representative high redshift, redshift 2 or so, low stellar mass sample. And so again, you have many more galaxies that are appearing with B over A close to 0.3 or 0.4, very elongated systems, linear looking systems, and there's a relative deficit of things that are rounder. All right, so as Anastasia mentioned, galaxies going bananas, where does that come from? It comes from this diagram. Okay, so with my collaborators, including Haowen Zhang, who was a visiting undergrad at Santa Cruz when I was there as a grad student, who did some of this work with Hubble early on, we looked at not just the 1D distribution of B over A, we looked at the 2D joint distribution of B over A as a function of size. Okay, and so you can see in this diagram, the galaxies in this representative high redshift, low stellar mass bin, they're tracing out a particular shape. And as you go to the larger size galaxies, they're preferentially showing up with smaller B over A, and there's a deficit of things with rounder B over A. So when we made this diagram, it reminded us of the shape of a banana. And so that is the inspiration for the title of the paper, Galaxies Going Bananas. Here are some images of these things from JWST Sears. So again, they're consistently, very linear looking, and in many cases, clumpy, like the old Hubble Space Telescope chain galaxies. And the main point that I have in this talk for you is just that there are way too many things at high redshift and low masses that look like this, that if you want to preserve isotropy, not all of these things can just be normal edge-on disks seen from the side. Okay, and the rest of this talk is kind of just going to fill that in. So I was not ready for the amount of press that this research would get, so I ended up on the front page of the New York Times back in January, which is a nice win for NASA and ESA, because how often is astronomy on the front page of the New York Times? Right? I did have some fun with it myself, so Columbia did a press release where I really leaned into the banana analogy, and then NASA and ESA did a press release with a beach-themed analogy. So galaxies are frisbees and surfboards and volleyballs and pool noodles and so on. This is all very exciting, but you have to be careful because of selection effects, as I mentioned, right? So the key thing for us in that context is this deficit of round galaxies at high redshifts and low masses, is that deficit actually real? Are we not seeing the galaxies because they're actually not there? Or is it some issue with the data or our analysis of it? Right? And so again, I already introduced this old puzzle, right? This fact that it's easier to see the edge on things than the face on ones. And so there's multiple ways to address this in the data. So one way you can address this is you actually, for the elongated galaxies that you do detect in your data, you can take your best fitting models, deproject them into the face-on view, recalculate the lower surface brightness, and ask how many of them would you have missed if they were instead seen face-on. And even with Hubble back in the day, Hubble would have missed maybe 20% of these edge-on galaxies reprojected onto the face-on view if they had stellar masses down to 10 to the 9, out to redshift 3 or so, right? And that's much lower than the actual 50 to 70% of objects that, as I'll show, actually look like this in the data, right? So, and JWST is now much more sensitive, so we expect this to be even lower. Another way to address this is you can just inject fake galaxies into your imaging and then rerun your entire source detection pipeline, right? And so when we do this for disks of various inclinations and surface brightnesses and redshifts in this B over A size diagram, down to the integrated magnitude, which we think corresponds to our lower stellar mass limit of 10 to the 9, out to redshift 8, we should have seen actually unreasonably large face-on axisymmetric disks if they were there, right? But we didn't. So now we have to interpret this puzzle. Of course, we are not sensitive to even fainter disks that are face-on, or even edge-on in some cases, but these probably correspond to even lower stellar mass galaxies that we are not going to look at for our analysis, for our 3D shape model. So I think that addresses this top left part of this landscape, and I think it's time for the field to maybe move on beyond this. And I have thoughts on further ways to address this, as well as these two things down here, but I want to spend the rest of this talk kind of honing in on this top right explanation of the 3D geometrical evolution possibility. So here are some examples, right? Simplified examples of 3D ellipsoids. The idea is we're going to approximate galaxies of different kinds of ellipsoids. So you got spheroids on the left, you got axisymmetric or circular disks in the middle, and then you've got these prolate ellipsoids on the right. If you're like me, starting out initially in this project, it's very hard to visualize these things in 3D. So let me offer the definitive analogy straight from New York City. Right? Start with a perfectly round ball of dough. Right? Flatten that ball of dough, which is a spheroid, along one axis, and you get the greatest thing in the universe. Pizza. I heard it. Yes. Now take that pizza and flatten it along one of the other two axes, and you get my other favorite thing in the entire universe, a breadstick. Or maybe in Europe, you guys would call this a baguette. I don't know. So this is what you should have in mind for these simplified kinds of 3D ellipsoids. And the key point is that a population of each of these kinds of ellipsoids is going to leave a very unique signature on that B over A versus size diagram. So take, for example, a population of spheroids. No matter which way you look at them, as Hubble mentioned 100 years ago, they're going to appear round in projection. So spheroids are going to appear near the top of the diagram with round B over A. Disks are different. You're equally likely to observe disks face on or in the edge on configuration, right? And so you actually get a vertical uniform stripe that trails off at low B over A because disks have a finite thickness. They're not infinitely thin. Right? And this last class of prolate ellipsoids is fundamentally different, right? Because they have two short axes. So they're kind of like this clicker. This clicker, you're much more likely to observe it like this, right? Or like this. And very rarely, when the viewing angle is just right, you'll see it like a small circle on the sky. Right? And so most of the projections of a population of prolate ellipsoids actually end up with large size and small edge on B over A, linear elongated structures. This should remind you of a particular fruit, a banana. Right? And so that's, we think, one of the solutions to the puzzle, that there's this new class of galaxies that are predominantly nearly prolate at high redshift and low masses. Right? And so the game now is to generate those kinds of histograms for millions of toy ellipsoids with many different axis ratios, and then to do a Bayesian inference, to reproduce, to find a linear combination of those templates for different ellipsoids that reproduces the actual observed distribution of the B over A size diagram for galaxies in a given mass and redshift bin. So I'll skip over a lot of the details, even though that's where all the beautiful work is, and I'll skip to, again, the results of this inference for one representative high redshift low mass bin. Here's the observed banana distribution in the JWST data. Here's one example realization from our posterior. You can see it looks pretty decent, right? But we don't just get a single best fit model, we get full posterior distributions, right? And there's really two key parameters that I want to focus on. One is the mean ellipticity of ellipsoids that correspond to this observed population of galaxies in this mass redshift bin. You can see that for this example here, the mean ellipticity is relatively large, right? 0.74 or so, which means that we can rule out the spheroid explanation as the dominant population giving rise to these, because we're not seeing them preferentially in the round shapes in projection. So now, with the high ellipticity, they have to be either a population primarily of these axisymmetric disks or these prolate ellipsoids or something in between, which are like these surfboards, oval disks. And the way to constrain between those possibilities is to constrain the triaxiality distribution, which for axisymmetric disks would be exactly 0. And instead, you can see that our posteriors are actually hitting up against 1 here, and that's what you expect for the prolate and triaxial scenarios. Right? So with this inference done over many different mass and redshift bins, you can try to back out the intrinsic 3D axis ratio distributions. I'll start with an example, lower redshift, higher mass bin, where we think, galaxies are mostly disks. Most star formation is happening in disks. Here is the short axis as a function of the intermediate axis ratio. These yellow colored lines demarcate roughly, axisymmetric disks would be on the lower right, spheroids in the top right, and then these prolate or triaxial things in the lower left. And you can see, again, redshift 1 to 1.5, higher stellar masses, galaxies in JWST data are roughly disky and spheroidal. Maybe there's some contribution of bulges. Makes sense. But as you move towards the high redshift, low mass universe, you start to see this distribution marching towards the lower left corner, towards the prolate or nearly prolate corner, right? And this is very surprising just in the sense because people have been doing this kind of modeling for decades. The most recent definitive analysis of this using extremely deep data from the Hyper-SupremeCam imaging and dark energy survey imaging and so on is from Aaron Cato Fong. This is low redshift, very low surface brightness, low mass dwarfs. And you can see they're basically primarily in the spheroid and disky part of this ellipsoid parameter space. Whereas, most of our objects at high redshift and low masses are down here. So now the key question, why should you care about this? Why is this important? This is not a rare population. So what I'm showing you here is the fractional contribution of prolate in blue, or nearly prolate in blue, these axisymmetric disks in oblate, and then these spheroids in green, the fraction as a function of redshift for these two lower stellar mass bins where we are not prior dominated. And you can see as you move towards high redshift, the contribution of the nearly prolate things is increasing to the 50 to 80% level. And another nice sanity check here is as you move towards low redshift, towards the left, in both panels, the contribution of the axisymmetric disks is increasing, which again is a nice sanity check because locally star formation seems to happen mostly in axisymmetric disks. So at this point is where all of you should be scratching your heads and asking, well, how can this possibly be right? How can this fit into our picture of galaxy formation? Right? This is bananas. Right? Let me try to address that in maybe the more familiar terms of the Hubble sequence. Right? I think what we're seeing here is the origin of the Hubble sequence. So one of the very first papers I wrote in astronomy was kind of doing an accounting of all the physical processes that can take a population of already established disks and turn them into ellipticals via mergers, right, instabilities, and then rejuvenation and gas accretion and stuff like that for these things. But the question is now, how do these early elongated galaxies fit into this picture? Here's how. We think galaxies start out elongated because they feel the influence of their environment. And then at some point, they've grown enough in mass and gas at the centers of their dark matter halos that they may undergo instabilities, right, that cause them to collapse into the central spheroid. And then it's around that central spheroid that you have this inside-out growth of the disk that we actually infer must be the case for many local galaxies. In this case, due to gentle accretion, maybe due to cooling flows, Andy is here, right, or gas-rich mergers and so on. So what do I mean when I say galaxies start out elongated because they feel the influence of their cosmic web or their environment? Well, the answer is the cosmic web, right? So here's a movie. We've all seen movies like this where under the influence of gravity, dark matter is collapsing along sheets and filaments, right? But I think something that's missing in the discussion is, in fact, halos themselves, dark matter halos themselves also start out nearly prolate as they're forming along these dark matter filaments. This is seen in some cosmological zoom-in simulations that are sufficiently high resolution that you can resolve this process, the formation of these galaxies. So here's one example from the Vela simulations. This is the dark matter at about redshift 2 or so. The dark matter halo itself is relatively prolate, and then the stellar distribution within it is also relatively prolate and aligned in the same direction as that of the dark matter. It's hard to tell from these movies, so let's look at this in another context, in this flattening elongation space, where for one of these halos, and the left is how the halo is evolving in the space for the dark matter, and then on the right is the galaxy stellar distribution. So the color coding here is just if it's red, it means you're at a higher redshift, earlier times when the stars haven't, when you're still dark matter dominated, enough stars haven't formed. So at high redshift, both the dark matter distribution and the stellar distribution in these simulations starts out relatively elongated, triaxial or prolate. And as you go towards lower redshift, as star formation proceeds, the dark matter halo becomes more spheroidal and the stellar distribution becomes more disky, like what we're familiar with. Right. With my amazing colleagues Farhan Hassan and Hawen Zhang, we've been using new techniques to quantify environments of dark matter halos and galaxies in the illustrious TNG50 simulations, which can maybe marginally resolve these things. It's a numerical experiment that's useful to try to use to understand this puzzle. So we've measured in particular this parameter that we call sigma fill, which essentially, when it's very low, it means a galaxy or a halo is forming along like a very thin tendril-like filament of the cosmic web. And when sigma fill is high, you're forming at a node of the cosmic web where, for example, a galaxy cluster or group would be. This is sigma fill in 5 different redshift snapshots from TNG 50 as a function of stellar mass, color-coded by the fraction of halos in these bins that are prolate. And you can see that as you move towards the high redshift, low mass things that are forming near these thin tendril-like filaments collapsing out of the cosmic web, that's where you see the high prolate halo fractions. And it's also where in these simulations you see now color-coded by the stellar distribution shapes, it's also where you see these elongated, nearly prolate galaxies. So how did I get into this topic in the first place? Well, back when I was in Santa Cruz as a grad student, with my advisors at the time, Joel Premack, Sandy Faber, David Kuhn, and Avi Shai-Deckel, we proposed that if this story is true, that galaxies are forming along filaments of the cosmic web, and they really do have this intrinsically nearly prolate structure that tracks the dark matter halo prolate structure, well, then they should be very strong intrinsic alignments. These things, these prolate galaxies, should basically point towards each other on very large scales, like light bulbs strewn along a string, tracing out the filaments in which they're forming, right? And again, this is further motivated by some of these simulations where these galaxies are seen. So this is showing the distribution of the alignment, cosine theta, of the alignment between the long axis of the stellar distribution and the long axis of the dark matter distribution. And then in blue is when the galaxy and the halo are both in the prolate distribution, and you can shapes. And so you can see in that early prolate phase, there's pretty much near perfect alignment internally on the scale of the dark matter halo between where the galaxy is pointing and where the halo is pointing. And the halo itself, of course, is pointing towards the dominant filament that it's accreting dark matter from. So I like to joke that it doesn't get much easier than this, right? A lot of people are interested in doing a lot of hard work to try to understand how galaxies are aligned with the cosmic web. It's very hard to observe that for disks, for example, because you have to go and measure the angular momentum vector and things like that. It doesn't get much easier than this. These are literally lines in the sky, and you can ask, do they point towards each other? And so back in 2019, I actually tried to look for this signal. We predicted a booming signal based on some mocks. You can see this excess of aligned pairs in blue on the left, but then with the Hubble candles data at the time, we did not see the predicted excess. We think this is due to various things, one of which is that is our sample selection. So there was a bias. We restricted ourselves to spectroscopically confirmed galaxy pairs, and it turns out there's a huge bias against getting spec Zs for elongated galaxies. And so this is an obvious thing to do next, right? Start a survey for this, and I'm interested in doing that with JWST or from the ground. But just a few months ago, some of my collaborators and I, so Avi Loeb, Guillermo Barro, Liz McGrath, Steve Finkelstein, and some of the Sears architects decided to revisit this puzzle of alignments, also now in the context of gravitational lensing, right? All this talk of elongation and alignments really begs the question, what is the role of lensing in this puzzle? Now, we are not working in these kinds of obvious cluster fields, right? We're working in blank deep fields where there is no low redshift bright cluster. So it turns out strong lensing is not that important. We show that. I'm going to skip over that. But what this puzzle is really intimately connected to is weak lensing by large scale structure, aka cosmic shear. Okay, and this is a really hard problem, right? Because what you observe with your telescopes are images like this, right? Noisy, pixelated images, and you want to go back and infer the gravitational lensing shear, but you don't know what the original shape of the galaxy was. Right? And this is really, can be a problem, because if high redshift, low mass galaxies have intrinsic alignments, and they're not just randomly oriented disks, for example, then interpreting, these shear maps can become more difficult. In this case, this is exaggerated. There's obviously some foreground lensing potential there, and so the orientations are correlated on large scales, and so this is fine. But actually, JWST is already enabling the use of source galaxies for lensing analyses, where the source galaxies in green have magnitudes and redshifts that fall in the regime where many of my colleagues and I are saying galaxies are intrinsically maybe already elongated. So Here is our attempt to try to connect to weak lensing, the community of weak lensing. So here is the footprint of the Sears survey. Every single little square here is an individual NIRCam chip. In every single NIRCam chip here, we have on the order of 50 to 100 background galaxies per square arc minute. Right? And what we're going to do is average over their orientations, right? In the same way that the weak lensing community does. If the orientations and ellipticities of background galaxies were not correlated in any individual chip, this summary statistic, this average complex ellipticity, should be less than 1%. These squares should all be blue, and what do you notice? Many of them are actually at the 10% level, right? So we can actually go in and look at some of these example chips where we see 10% or larger average complex ellipticities. So here are 3 examples. It's hard to tell by eye, but if you're like me and you've stared at this long enough, you start to see interesting patterns, right? You start to see these interesting, like circular, almost polarization type patterns. In some cases, like these large chains of objects, right? And so the bottom panels here show the statistical way to address this. So for every single individual chip, I basically create 1 million realizations where for every individual galaxy, shown by a rectangle here, I assign it a random orientation. And then I recompute the summary statistic under the null hypothesis of these randomly oriented background galaxies. That gives you the blue distribution. And then the red line is the actual observed statistic from the actual alignment pattern. And you can see in these 3 examples, we are way out in the tail of the null distribution. So these are not random alignments, even though it's hard to tell by eye. You can do the averaging on even larger scales. So here's an example of a module, so pairs of 4 NIRCam chips, 1/2 of a single JWST pointing, where now for high redshift, low mass elongated galaxies, hard to tell by eye, but there are non-random alignment patterns here, as shown by this null distribution and then the actual observed statistic. And then one more level of averaging over entire JWST pointings. Here's an example of a high mass bin in one of these JWST pointings in Sears, where again, you see lots of these non-random alignment patterns. So there's a few different explanations for this. One is there could be, even though Sears was selected to not have any obvious galaxy cluster right, at low redshift, there could still be overdensities at high redshift, right? And actually in the mid-2000s, it was all the rage to use the Hubble Space Telescope to look for these dark lenses that could be responsible for lensing in blank deep fields. And so we're suggesting we should maybe go back with JWST and revisit that. And in fact, in our case, we do see an overabundance of massive galaxies at about redshift 0.75. And if this is part of a protocluster or a filament at redshift 0.75, then you can actually explain this 10% average complex ellipticity as a cosmic shear from this protocluster or filament. This might sound insane, maybe, but it turns out that actually the very first detection of cosmic shear from space with the Hubble Space Telescope was in the parent field of Sears. Here's a nice paper from the early 2000s by Rhodes et al., which shows the shear map along the much larger version of this elongated strip than Sears is a very small fraction. And then in the late 2000s, Moustakas et al. Had a very nice paper where they actually found 3 strongly lensed systems just outside of the Sears JWST footprint. And when they did the source lens reconstruction of the image of these images of these lens objects, they required 10% external shear, in addition to the lensing potential of the massive lens galaxy. So is it a coincidence? I don't know, but it definitely deserves further scrutiny. Another thing, as I already mentioned, is the intrinsic alignment hypothesis, right? So for this, we really need to get spec Z's and ask in these chips, modules, and pointings where we see these alignment patterns, what is the redshift distribution? Do we see any examples of large pairs, sets of galaxies that are close together also in redshift space in the 3D direction? So maybe they live on the same large-scale structure or filament at high redshift. And then the last thing, of course, is there can always be systematics in the data or in our measurements. And so we think we rule that out using foreground Milky Way stars in Sears as a null test, because the stars should not be aligned, they should not be sheared, right? And so here is our average complex ellipticity, and then something called the shear variance as a function of scale. These black lines are actual galaxy alignment measurements, and then the colored lines are the measurements from the stars and the different NIRCam filters. And so, there are some systematics, but, our measurements, especially at the chip scale, are way above these null lines from the foreground stars. All right, in the last maybe 5-10 minutes, I'm gonna leave you with some teasers of what's coming next. And the main thing you're gonna notice here is that I think further progress in this field is gonna require interdisciplinary collaboration. I've been here this week talking to many of you on lots of cool possible collaborative projects. So the very first thing is I didn't really talk about strong lensing too much, but it's going to be very interesting to look for examples of high redshift galaxies in this low mass Milky Way progenitor regime that are strongly lensed. And there's already a famous example of this. It's called the Firefly Sparkle by Lamia Mola and Karthik Iyer. So here, this is in a strongly lensed field. Here it is. It's very clumpy, right? And if you reconstruct what this galaxy might look like in the source plane, here it is in the original source plane, pre-lensing. And so it's, again, very clumpy, multiple clumps that I actually have more than 50% of the mass and light compared to the total galaxy. It's very hard to see from this projector, but you should notice that there's a diffuse background emission from stars that is elongated. So this could be one of the galaxies at redshift 8 that, in unlensed deep fields, we're seeing, it could be the analog of a higher redshift lens analog of these very elongated prolate candidates that I mentioned. And this is very exciting, connects to work actually that Vasily is doing here at the IOA. Beautiful work trying to use very low metallicity stars in the Milky Way today to infer the Milky Way's assembly history, right? And so there's evidence from Vasily's work already, right, that the Milky Way may have formed its disk earlier than normal, but it had this early, what he calls chaotic or possibly filamentary phase. And so I think I've been trying to find connections between my work and galactic archaeology, because I think it's very cool. Another thing that needs to be said is, baryonic physics is not well understood, but there's a connection to dark matter phenomenology, and actually Anastasia does amazing work on this, right? So here's a work that I was not involved in, did not even know it was happening, came out in the archive, where they basically took images straight out of my paper, and then they used these paired simulations of fuzzy dark matter, warm dark matter, and cold dark matter to show that in these alternative dark matter scenarios, it's actually much more easy to produce these elongated galaxies, whereas in CDM, you end up with relatively rounder galaxies when you consider population statistics. And again, this is building on the pioneering work that Anastasia has done, so using really her simulations with Phil Moog's and Tibor Dome and others, where again, these simulations also let you do new stuff in the future to talk about the large-scale connections to filaments, for example, possibly, at early times. Whereas you see in CDM, the stars that form are relatively like in these isolated, knotty type configuration. In these alternative dark matter scenarios, you get star formation along basically these filaments. AI is going to be very important. I'm involved with some work actually already trying to do self-supervised learning to try to pick out where these galaxies might live in high dimensional parameter space of observables. And so the nice work by Jesus Vega Ferrero trying to learn without labels, without visual classification labels, which can be misleading sometimes, where these things are in the Sears data and also in simulations. So stay tuned for work on that. And then the last thing I'm going to end with is galactic dynamics. This is like where all the really beautiful stuff is, in my opinion, because as we learned over the past few decades for local massive elliptical galaxies, right, you can get, so this is the rotational support parameter, essentially, as a function of the projected ellipticity of galaxies, right? You can get highly flattened galaxies that need not be supported by rotation, right? You can get highly flattened galaxies that instead are supported by dispersion, right? Prolate ellipticals, essentially, right? And so I'm going to just leave you with a teaser of some stuff that we're doing to try to address this from the kinematic side. So with an amazing undergraduate, Arnav Shah at UT Austin, along with my collaborators Raymond Simons, Anthony Taylor, and Steve Finkelstein, we've been trying to ask, well, what can gas kinematics teach us about these 3D shapes of these early galaxies? So one interesting thing is if you have a gas disk and a stellar disk, the two are on average going to be aligned, right? But if you have a gas disk in a prolate stellar system, there is no preferred orientation for a gas disk. You're going to have much more misalignments between the gas disk and the stellar prolate system. And in fact, the gas may not even be a disk, it may even be filamentary. And so these two things are going to leave you with very unique signatures on a plot of the gas velocity dispersion or emission line width as a function of the axis ratio of the stars. So the gas disk in a stellar disk scenario in orange gives you this line width viewing angle relation, right? But we expect a lot more scatter and possibly a bias for this scenario, and then we expect a different scenario for filamentary gas in these prolate stellar systems. And so we've been using some very deep data from Sears and Rubies to fit basically emission lines, which is uniquely available for these high-redshift galaxies in the red-stream optical wavelengths with near-spec. And then we have some very preliminary work, so don't take this too seriously yet. So this line width B over A dependence for low-mass galaxies is relatively flat. Right? This is only a few points, so we're trying to get more galaxies from different surveys. And then for the more massive galaxies that we think should be able to sustain a disk, we're seeing maybe tentative evidence for this orange, line width B over A relation. But there's not that many galaxies, so we're now trying to get more data from the archive and also putting in proposals, which are due next Tuesday. But the gas is never going to be definitive, so the very last thing I want to leave you with is the smoking gun signature, the smoking gun test, and that is constraining the orbits of the stars in these galaxies. Okay? So if you show me or anyone in this room an image of one of these high redshift Milky Way progenitors, like this one, I cannot say, and no one in this room can say for sure, just from the imaging alone, that this thing is an edge-on axisymmetric disk, or this thing is a triaxial thing, or a prolate thing, or mergers, or unstable or stable, right? The way to do that is you have to constrain the orbits of the stars. If this is an edge-on disk, most of the stars should be on circular orbits. They should avoid the center. That is not possible if these things are instead primarily triaxial or prolate. Instead, the dominant kinds of stellar orbits that you get for those kinds of systems are things like these pretzel or fish orbits that go through the center of the system. You get these boxy orbits that, again, unlike the circular ones, they go through the center of the system. And I swear I'm not making this up. You get banana orbits, right? And you put two of these things together side by side, you get the famous X shape that we see in some local bar galaxies. So this is basically borderline impossible to do with current facilities. It's going to be possible with the extremely large telescope that you're developing here in Europe and that we're trying to develop in the US with the GMT and the TMT, because then they're going to enable us to do IFU spectroscopy and constrain the stellar kinematics across the face of these galaxies. Until then, I've been compiling some extremely deep spectra from Keck and JWST, where essentially we put a slit along the long axis of the elongated galaxies, and we're trying to take the very first census. If you can detect the stellar continuum, and then resolve and detect the absorption lines from the stars in these galaxies, how many of them do you not see evidence of a velocity gradient? No one has ever done that. And so we're working on it actively. I don't have results to show you in this colloquium, but ask me more if you're interested. And then we're also working on the really old school way of doing this, and that is elliptical isophotal fitting and characterizing the surface brightness, the isophotal shapes. Because before you can get spectroscopy of even the local giant ellipticals, if you look for evidence of like twisty and boxy isophotes, for example, that tells you something about the orbits that the stars are on in galaxies, just from the imaging alone. So stay tuned for this exciting work on stellar dynamics in the next year or so. And I will stop there and summarize. I hope I've convinced you that galaxies start out elongated. They may be prolate or triaxial. This is naturally expected even in lambda CDM if they're forming along cosmic web filaments. And we think we're seeing evidence for high redshift alignments of these galaxies on very large scales. And so stay tuned for a lot more work on this. Okay, thank you so much. I'll stop there, take questions if you have time.